Hey folks, just checking if everything is okay. Just give me a sec. Yeah, we are live now, I guess. Just give me a sec. Just wanted to test if everything is okay. Just checking if everything is okay. Just give me a sec. Yeah, we are live now, I guess. Okay. Yeah, we are a couple of minutes early, but that's okay. Let's chat for a while others join in. Just give me a second. Okay, yeah, everything looks good now. So yeah, okay. Today we'll be solving the dynamic programming problems. Yes, I do understand that dynamic programming problems take a little longer to solve than other problems. So we'll also give you detailed solutions. Hi folks, thank you for joining. So today we'll solve the dynamic programming problems practice session. And we have already uploaded some greedy algorithms also today. We are hoping to finish most of the content by tomorrow, worst case day after tomorrow. So let's I think we're mostly there. We're just editing some videos and then place them. So a couple of thoughts that we had were as follows: that we would spend a few days just revising whole of data structures algorithms, also doing two subject tests, right? So we were planning to have two subject tests of 1.5 hour length, which will cover all the topics in data structures and algorithms. And we'll have these tests before the end of April 2nd, because we were planning to start C programming from April 3rd onwards. So that today is 20. What day is today? Today is 27th, right? So 28th, worst case by 29th, we'll be done with all the contents, with all the practice problems. So maybe 30 and 31st or 30th and 1st, we can spend some time on these subject-wise tests. The subject tests, we'll have two subject tests of about 30 problems each, 1.5 hour, 1.5 hour. That's right? We'll send out these tests to you over email. And we want you to revise whole of data structures algorithms. We'll get started with C programming from April 3rd. Just wanted to make that clear. And we were also designing the the detailed plan so as to finish for batch 1 by late August or early September, and batch 2 will try and finish by late September. Okay, so just wanted to call that out. And we also understand that some of you who are final year students, final year BTech students, also have exams. Who are in your third year BTech, who are preparing for next year GATE, could have exams in late April and early May. So we'll also accommodate for that and give you much more easier content. So yeah, so that's the plan. I just wanted to share that with you. So yeah, let's get going with these practice problems. Yeah, some of these problems are very lengthy. So another thing that I noticed is there are fewer problems which are tedious solving, which involve tedious solving in dynamic programming, because it takes a lot of time to solve some of these problems, because you have to draw the whole table, solve the whole problem bottom up manually, and that could take a lot of time. But there have been instances in the recent past where dynamic programming problems have been actually given in GATE, and hence we thought we'll cover them exhaustively, right? So yeah, let's get going and let's actually see the solutions. I'll change the screen now. Just give me a second. I'll change the screen now to the screen share mode. Okay, so I'm on the screen share mode now. Yes. Okay, so let's get going with the problem. Okay, so let's get going with each of these problems. I hope the font size now is okay. I hope there are no major issues now. So let's get going and let's start solving this stuff. Okay, so I'll solve from problem 1 to problem 15, and let's get going. This is just like the old days. So match the following dynamic programming implementations in list 1 of problem with the time complexity in list 2, right? So we have seen all of these problems. We have seen matrix chain multiplication, TSP or traveling salesman problem. We have seen 0-1 knapsack and Fibonacci numbers. We have seen all of them, right? It's very easy to figure that out. I mean, the simple giveaway is, if you see, traveling salesman problem we know is exponential time algorithm, right? So for B, it has to be 3. There is only one option here where B and 3 are matched, if you notice. So first option has B matched with 3. Rest everything has B matched with other values, right? We already know. So even if you don't recall the time complexities of all of them, if you just know the TSP's time complexity to be exponential, you're good, because option A is the right option here. And you can eliminate all other options by just realizing that B and 3 are to be obviously matched. Okay, very simple. You can actually solve it in 10 seconds if you're careful. Okay, so option A is the right option here, right? So very simple problem. Now let's go to the second problem. Okay, so the second problem says that so you're given a knapsack that can carry a maximum weight of 60 kilos, let's say. There are 4 items with weights 20, 30, 40, and 70. And these are the values of these items. What is the maximum value of the items you can carry with the knapsack? Here the fundamental assumption that is being made is that this is a 0-1 knapsack problem. Okay, we should add that to this problem. I think we didn't call it out because there is an other problem called as fractional knapsack that we discuss in greedy algorithms, right? So this problem, if that is not clearly mentioned, that you can either take a whole item or not take a whole item, right? That has to be mentioned for it to be a 0-1 knapsack. In this context, we know we are solving dynamic programming problems, and we know that 0-1 knapsack is DP, while a fractional knapsack is a greedy algorithm, which is different from DP. So here it's a 0-1 knapsack problem. Okay, we'll edit this question to make it more accurate and more meaningful. Okay, so I know the capacity is 60, which means item 4 cannot be there because item 4's weight is 70, right? So item 4 can't be there, right? What other possibilities are there? Let's assume this is item 1, 2, 3, and item 4. I can have item 1 and 2 because the total weight is 50, or I can have item 1 and 3. Can I have item 2 and 3? No, that's not possible, right? Because the total weight of item 2 and 3 is 70. So these are the only 2 valid possibilities. Of course, I can solve this by drawing the DP table, all of that, but that will take a lot of time, right? Instead of drawing the whole DP table, right? It's much faster for me to quickly look at these numbers because I have only 4 items. I can quickly evaluate all the options that matter. So if I take 1 and 2, what is the value? 70 plus 80, which is going to be 150. If I pick 1 and 3 items, then the total value is going to be 70 plus 90, which is 160, right? No other possibility exists because you can't pick 2 and 3. If you notice 2 and 3, if I pick, the total weight is 70, which is more than the capacity of my knapsack, right? Again, I can't have item 4 because item 4 itself has 70 kilos weight, right? Which is more than the capacity of my knapsack. So obviously the answer here is 160, which is option A, right? Sometimes when you have these DP problems with just a few items like this, it is easier to just exhaustively list all the possibilities and manually solve it. This tends to be faster than actually following the DP based tabular approach with a bottom up scenario, right? So that's important because you have to solve this problem as fast as possible, right? Okay, so problem 3, let's go to problem 3 now. Okay, so we discussed this as one of the applications actually, if you recall. So DNA sequences can be viewed as strings of AGTC characters, which represents nucleotides. Finding the similarity between 2 DNA sequences is an important computation performed in bioinformatics. Given 2 DNA sequences SNT of length 7 each, what is the length of the longest common subsequence? So when we were learning the longest common subsequence, we learned that one of the applications of LCS is in finding gene sequences or finding common subsequences in gene strings, right? This is the exact problem. Now, if you notice, I'm given 2 strings S and T. Now, of course, this is your longest common subsequence problem, right? Now, how do you solve this problem? First, you'll have to always remember, or you'll have to be able to reproduce the recursive equation, right? The LCS, the length of the longest common subsequence of 2 strings of lengths M and N is equal to, so this will be equal to length of the length of the longest common subsequence of length m minus 1 and n minus 1 plus 1 if my s of m is equal to t of n. So if the last character in s and the last character in t match, this is the option. Or else the option will be max over the longest common subsequence in m minus 1 comma n and longest common subsequence in m comma n minus 1, right? So we've already seen this recursive relationship, right? We have already seen the recurrence relation like this, right? We have also seen an example. If you recall, we have also seen a solved example, which is actually a previous year GATE question, right? So we've already seen, so by using this recurrence relation, I can start constructing a table. Of course, drawing the table right now will take a lot of time. So what I've done here is I pre-drawn it, right? So let me just show you the table that I have. Just a second. I have pre-drawn this table. Yeah, so I have pre-drawn this table here. Let me just scroll down. Okay. Again, we'll share this detailed notes with you, right? So I've already pre-drawn this table from for both these strings. And if you notice, if I apply the recursive, if I apply the LM, the recursive equation that we have seen the recursive equation, right? We have also written it down just in the previous slide, right? So this recursive equation, if I keep filling up my whole matrix using that, right? We saw that, right? For LCS, we saw the recursive equation. It will be max of this comma this, or if they both match, it will be 1 plus this. We saw a worked out example, right? In the course videos. So same thing. You basically fill this matrix. It will take non-trivial amount of time to fill it, but eventually you'll see that your both strings, the first string of length 7, the second string of length 7, have a common subsequence of size 5. Okay, because this table at the end of it, this literally tells you the LCS between both of your strings with full length m and n, right? So we'll share a Google Doc with these solutions so that you can also work it out in your spare time and verify your solution. Please try and solve it on your own first. Okay, but all you need to know, to be honest, all you need to know here is simply the recursive relation, right? If you know the recursion formula, right? If you know this recursive formula, that's it. You can start filling that matrix. And we have solved an example in the course videos also. Okay, step by step, we solved it. Just repetition of the same thing on a different input. That's it, right? So the answer here is B, which is 5. Okay, because the table, when I constructed the whole table, we got a value of 5. Okay, sounds good. So now let's go to question 4, right? Yeah, so let's go to question 4 now. Okay, so this is a question. This is an interesting question, actually. So, okay, this is a very interesting question. So, this is one of the topics that we didn't cover in detail, but I'll explain you here anyway, since this question came up. Actually, some of these questions are not in GATE, unfortunately. We couldn't find too many questions in GATE. So we have taken these questions from standard textbooks. So we have taken them from standard textbooks, or from some of them we created from scratch, right? And some of them we have taken from standard textbooks, right? So, okay, let's look at this problem. It says, consider a matrix chain multiplication problem. If the dynamic programming gives a table S as follows, table S contains the splits of optimal parenthesization. What is the optimal parenthesization? So the splits table, so let me define the splits table, okay? So the optimal, so if you recall, how does the matrix multiplication recursive equation look like? Right? To multiply matrices AI to AJ, the cost of multiplying from matrices AI to AJ is equal to 0. We studied this, right? It's equal to 0 if I equals to J. Otherwise, it is the minimum over all the values of K from I up to J minus 1. Okay, so let me erase this. So let me erase this and write it down. So let me erase this and write it down more clearly, right? It is the minimum over values of K such that K is greater than equal to I, but less than J, right? All these possible values where M, right? What am I saying here? When I have matrices AI to AJ, if I use AK as the split, then the cost of matrix chain multiplication is from AI to AK and AK plus 1 to AJ. So this plus the cost from K plus 1 to J plus the cost of multiplying both these matrices, which is Pi minus 1 multiplied by Pk multiplied by Pj. And this is true if I is less than J. Right? This is the recurrence relation that we have already studied, right? Look at it. It's actually very easy to remember or to even understand this recurrence relation if you understood how they were derived at. Okay, this is a simple base case. Otherwise, I'll try to split this at some vertex K, right? So not vertex, sorry, at some intermediate matrix K, such that K lies between I and J, and I'll compute the total cost. Now, while doing this, here is the fun part. While doing this step, right, you can store another matrix called Sij, which is called the split matrix. Okay, this is called the split matrix, which stores the value of K, which means what does it store? It stores for Aij, from Ai to Aj, when I'm multiplying it, whichever K I actually split this, that value I will store this, and this matrix is called the split matrix. Okay, and what we are given here is the split matrix. Okay, and if this is the case, of course, the split matrix will have, in this case, Sij equals to 0. Right? In this case, whatever is the K that minimizes this, okay, whichever K minimizes this, that K I'll place in Sij. Okay, so this is called the split matrix, and it will help us actually get the actual splits. So let's actually see this whole thing, right? So here I have a matrix chain problem with 4 matrices, right? Here my I goes from 1 to J, and my J goes also from 4 to 1, right? So what do I have? I have A1, A2, A3, and A4. Now let's look at A14. Okay, this is my matrix S, right? S14. What should S14 store? S14 will store the index of the matrix where the split has been taken place when I'm multiplying from A1 to A4. Right? Where did this split take place? At 1, which means this is one matrix and this is the second matrix. Right? Now, what am I left with? A1. This is a single matrix, so nothing to worry. What am I left with now? A2 to A4 I want to multiply. So I'll go from S2, right? I'll look for S24. Now S24 will give me the split at which this product was split. Right? That's how we are defining the split matrix, right? So S24 will contain value 3. It contains value 3. That implies that the second parenthesization that I have will be like this. This is the second parenthesization that I have. Right? Now everything is good. I multiply A2 with A3. The resultant I'll multiply with A4. The resultant I'll multiply with A1. Okay, let's look at which of these options now satisfy this. I multiply A1, A2, the resultant with A4, then with A1. Right? That's it. This is option A is the right option here. Right? The split matrix here. The split matrix is something that is defined like this, which basically stores. Actually, this question could have been more detailed and explain what split matrix is. Okay. Some books use this terminology where they call this as the table of splits or split matrix. Some books don't even cover this topic in detail. Okay. I'm glad this question was asked and we could cover this topic here. Okay. So the answer here is A. Okay. The split matrix is basically storing the optimal K where the split for multiplication from AI to AJ would take place. Okay. I hope this is clear. Okay. So now let's go to question 5. Okay. So let's go to question 5 now. What does it say? It says given dimensions P0 to Pn corresponding to a matrix sequence A1 to An, where AI has these dimensions, determine the multiplication sequence that minimizes the number of scalar multiplications in computing A1 to A4 with these values. Literally, you have to solve the matrix multiplication problem with splits, right? To solve this problem, what do you need to do? You have to do this recursive equation, right? Mij, and you also have to compute Sij that we just discussed. Look at this. For this problem, you will basically use this recursive equation to compute Mij values, and you'll also fill the Sij values. This is literally given a bunch of numbers. You have to fill these two using the recursive formulation. Using the recursive formula, okay, you have to manually go do a bottoms up DP manually, right? Of course, this is time taking. So what we have done is what I've done here is I've actually solved this and placed it here so that it's easier. Okay, so you can actually see this. This is what you will get. So if you build the dynamic program, these are MIJ values, right? These are MIJ values, right? If I compute MIJ values, this is what I would actually get, right? I would get a cost of 158 as the total cost of matrix multiplication. And that would come from, again, here I've not drawn the Sij matrix, but you can draw the Sij matrix also while you are filling the Mij matrix. Okay, just like this Mij matrix, you'll also get an Sij matrix. From that, you'll notice that the total cost is 158, and you'll get it by multiplying A2, A3, the result with A1, finally the result with A4. Right? This is the chain of multiplications that you have to perform. Okay, of course, filling this is non-trivial. It takes considerable amount of time. Okay, just to save time here, I've already pre-computed all of this, and this is the solution that you would get. Right? So let's go back to, so A1, A2 resultant with A2, A3 resultant with A1 and A4. Right? So let's go to the options that we have. So A1, A2, right? A1, A2, the resultant with A2, A3 resultant with A1, the final resultant with A4. So option C is the right option here. Again, this is a tedious problem where you have to literally build the whole dynamic programming table from bottom up. Okay, very time taking problem. Okay, so the next problem is interesting. Okay, let's go to the next problem. So sixth problem, right? Okay, so the sixth problem is, oh, okay, again, here I'm given, okay, again, it's very similar problem. I'm given some parenthesization of matrices, and these are the sizes of each of my matrix. My first matrix is 2 cross 5, my second matrix is 5 cross 10, third matrix is 10 cross 3, fourth matrix is 3 cross 5, fifth matrix is 5 cross 7. It's asking what is the cost of optimal parenthesization. Okay, again, you take these numbers and you solve it manually. Okay, you construct your Mij table. Here you don't require Sij because it's only asking for the cost. It's not asking for the exact sequence of multiplications or parenthesization. So when you solve it, again, I tried to solve it beforehand because otherwise this would take forever, right? So sixth problem, yes. Oh, we also computed the Sij table here. Okay. So if you compute it, you'll get a cost of 260. Again, this is your Mij table and this is your Sij table. Okay, you also get the parenthesization here from your Sij table. Right? Of course, you have to start filling this. This is all the values of I. This is all the values of j. You go step by step and start filling it. Okay, when you start filling it, you'll get this. Again, this has to be filled using the recursive equation for Mij. It's time taking. I completely understand. It took us considerable amount of time to solve this manually. And the final solution is 260 here, right? So yeah, for some of these problems which are tedious to solve live, because the answer is 260 here, right? So for some of these problems, you've already pre-solved it and put the tables there so that you can verify when you solve it, right? The core idea for most of these problems, the core idea for most of the problems is to know the recursive equation. Here is a very interesting problem. Okay, let's go and tackle this problem. Right, so this problem is, assume that you have a chocolate bar of length 5 inches. You have a satisfaction chart that indicates that if you eat a piece of length I inches, then you get a satisfaction of Si. So I'm given this table which says, if I eat the chocolate which is just 1 inch long, this is my satisfaction. 2 inches long, this is my satisfaction. 3 inches, 4 inches, 5 inches. We can assume that all quantities involved are positive integers, right? You want to decide using dynamic programming. They're already telling us it's a dynamic programming problem. Okay, what is the best way to make pieces of your chocolate bar so that you get maximum satisfaction when you consume the bar, right? Literally, I have a bar which is 5 inches long. Okay, let's say this is 0 inches, 1 inch, 2 inch, 3 inch, 4 inch, and 5 inch, right? I can cut this bar in multiple ways, right? I want to cut, I could cut one piece each, or I can cut a piece of size 2 or size 3, size 4 or size 5. And when I eat a piece, this is the satisfaction that I would get. Now the question here, this is a fun question. Now the question here is, so let's assume my 5 is equals to n, right? Let's assume I can, again, remember that I can only cut 1 inch. I can't cut 1.5 inch and all of that stuff. Okay. Find the maximum satisfaction possible when you consume the whole bar, right? So it's a very good problem. So this is also called as the rod cutting problem. This problem is a very, very standard dynamic programming problem called rod cutting problem, right? So the reason we have not covered this in the course videos per se, or at least as of now we have not covered it, is because this has never been asked in GATE. Okay, so we have to make choices. There are hundreds of DP problems. There are hundreds of dynamic programming problems that are there in literature, right? It's almost impossible to cover all of them. Okay, but we gave a decent size of them. So this is a rod cutting problem which is not yet asked in GATE, and hence we did not cover it in detail in the course videos. But if you have understood dynamic programming, if you have understood the core foundations of dynamic programming, this problem is solvable. Okay, if you think about it, if I have 5 inches, if I have n inches, how many cuts can I make? I can make at most n minus 1 cuts. Right, look at it. I can either cut here, or I can cut here, or I can cut here, or I can cut here. There are 4 places where I can cut when I have a 5-inch chocolate bar. Right. So since I have n minus 1 cuts that are possible, if I do a brute force, way of solving this problem, I will have 2 power n minus 1 cuts that are possible. Okay, this is the brute force solution. Okay, now let's try and design a dynamic programming solution to this problem. Let's solve the dynamic programming problem. Okay, so let's go step by step and solve it. Okay, let me define it here. Let's say that I have RI, right, which is often referred to as revenue or satisfaction. Okay, so RI is the maximum revenue or the maximum satisfaction in this case, or the maximum satisfaction in this problem case, in the chocolate bar problem, right? It's a maximum revenue or maximum satisfaction achieved by performing up to, I can either perform 0 cuts, 1 cut, 2 cut, 3 cut, up to I minus 1 cuts. By performing up to I minus 1 cuts, right? Look at this. I'm defining RI to be the maximum satisfaction achieved by performing up to I minus 1 cuts. I could either perform 0 cut, 1 cut, 2 cut, whatever it is. Amongst all of them, I have the maximum satisfaction written as RI. Now let's write the recursive formulation for RI. Right? So RI can be written as max over, right? It can be written as max over Pi. Oh, again, before we go there, I have to tell you the problem structure. Okay, I forgot to tell you the problem structure. So here Pi, here Pi is nothing but the satisfaction I get from, so Pi is nothing but SI here. Okay, so I'm trying to write a formulation which is more general. For the rod cutting problem, this is called revenue, and Pi is the length of length of the ith cut. Okay, so sorry, the value of the ith cut, sorry, not the length, right? So now look at this. So whatever they're calling it as SI, I'm calling it as Pi here. That's it. Okay, so now if you notice, the maximum satisfaction or revenue that I'll make using up to I minus 1 cuts is cutting at the ith point, right? It is a satisfaction. Here I have no cuts. What does this mean? This means I have no cuts at all, right? So what will R5 be? Imagine if I'm trying to perform R5, right? If R5 equals to P5, that means I've made no cut at all, right? So the revenue or satisfaction that I would get, right, by having up to I minus 1 cuts is I could have 0 cuts. This is the case where I have 0 cuts, where I have taken the whole brick, up to I. The satisfaction that I get from this, I'm writing it as Pi. It is max over pi comma. This is one possibility. Second is making a cut at the first point plus r of I minus 1. So I've made one cut here at the second point, sorry, at the first point, right? This is the value that I would get, or satisfaction that I would get by making a cut at first point, and plus the revenue or satisfaction that I would get by making up to I minus 2 cuts, comma, P2 plus R I minus 2, right? Plus, sorry, comma, P3 plus R I minus 3, so on so forth. P I minus 1, R 1. This is the recurrence relation for rod cutting problem. Okay, this is the recurrence relation for rod cutting problem, right? So here pi is nothing but my SI here. Remember, pi is nothing but my SI here. That's all. Okay, whatever you have as SI, I'm reading it as pi, because in the general rod cutting problem, this is the value that I would get, or this is the satisfaction that I would get by making a cut at the ith place, right? And this is the revenue or satisfaction that I would get by performing up to I minus 1 cuts, right? And if I have this recurrence relation, notice one more very important thing. To solve a problem of size n, Rn, see, what do we want to find finally? We want to solve Rn, right? Because we want to make up to n minus 1 cuts, right? Because given a chocolate bar of length n, we know we can make up to n minus 1 cuts, right? So this is the problem that I want to solve finally, right? So a problem of size n can be written as a problem. So here I don't have to solve any subproblem. Here I have to solve a subproblem of size n minus 1. Here I have to solve a subproblem of size n minus 2. Here I have to solve a problem of size n minus 3, so on and so forth up to a problem of size 1. Now again, if you notice, to solve this, I have to solve a problem of size n minus 3, n minus 4, so on and so forth up to 1. Now if you notice, this n minus 3 is here, this n minus 3 is also here. So there is an overlapping subproblem here, right? Because of this overlaps, right? So we have already seen optimal substructure. We have already seen optimal substructure here by defining the satisfaction recursively like this. Here I am seeing the overlapping subproblem. Okay, here I am seeing the overlapping subproblem, right? Which means this problem can be solved using DP. Okay, because I have both of them. So I'll also solve this using bottom-up DP. Okay, I'll also solve this using bottom-up DP. Okay, now let's go back. To our, so to solve this problem, again, I've written down the solution here. Actually, to solve this problem is much easier. I don't even have to do DP. Okay, so to solve this problem, right? So actually, let's solve it without even DP. Okay, let's solve it much more easily. Okay, let's look at the problem that I have. Okay, so just let me open so this is the whole thing. 1 second, just give me a sec here. Okay, so if you look at this, right, I have all of them, right? So if you see my total, I have to break something which is of length 5. In how many ways can I break it? I can make one break at 1, then at 2, then at 2. I can break this into 3 pieces like this. This is one possibility, right? So if I have this possibility, so there are multiple possibilities like this. If I make my cut at 1 and then piece of length 2 and piece of length 3, all three of them sum up to a piece of length 5. So this is 3 plus 7 plus 7, right? 10 plus this is satisfaction of 17, right? Similarly, if I keep solving this, see, this 5 can be broken down into a piece of size 2 and a piece of size 3, right? Here I'm not even applying DP. I showed you the recursive relation for rod cutting so that you will be able to understand and appreciate that given new problems also, if you think carefully, you can write the DP formulation. Of course, it's not trivial. It takes lot of practice, and it takes a lot of time also to actually work it out. But for this problem, if I don't want to solve it using the whole DP approach, I'll just do brute force, right? Because imagine if I have a chocolate bar of length 5, I can break it into a chocolate bar of length 2 and 3, wherein my total satisfaction will be 16. Or I can break it into chocolate bar of length 1, 1 and 3, right? Now satisfaction is 15. Or I can break it up into chocolate bar of length 2, 2 and 1, wherein my satisfaction is 17, right? Or I can keep the whole bar intact without making any cut, right? Now my satisfaction is 12. These are the only 4 options, valid options that we have, right? Now, which of them has the maximal satisfaction? The third option. When I make it into cuts of 1, 2 and 2, right? That's a total of 17, right? So I just worked out these cases so that I don't miss anything when I'm actually solving it and to avoid silly mistakes, right? So the option here is 17. Now the important thing here is, please note that I'll share the document, we'll share the solution document. The reason I'm not working out the exact details of each of these DP is it will take, like, you must have seen this, right? We have actually worked out some of these DP problems as solved problems already, right? For every DP problem, we added this solve for most of the DP problems, right? We have actually added how to compute how to actually solve it using bottom up. And if you notice, each of those videos is like 20 to 30 minutes long, right? If you start doing that, this whole session will take hours to solve. Okay, that's why I'm avoiding it here, but we'll share the document so that you can actually do it on your own. I understand this takes a lot of time. You got to be patient, and it's very, very prone to silly mistakes. That's why I've written the solution so that I don't make mistakes, because it's just about enumerating. And even if I forget one enumeration, I'll make a mistake, right? That's why I wrote down answers for this live session, just to be on the safe side, not to miss anything. Okay, so now let's look at 8th problem, right? Okay, so let's look at the 8th problem. So consider a variant of the subset sum problem. Okay, there is a variant of the subset sum problem which says, given a set of n non-negative distinct integers and a value m, right? Determine if there is a subset of the given set whose sum is divisible by m. Okay, this is a good one. Okay, which of the following statements is true with respect to the above problem? Let's actually start solving this. Suppose my set is this. Okay, this set has 4 elements and the m is 6, right? It's asking, is there any subset here whose sum is exactly divisible by 6? Okay, if you notice, is there 7 plus 5? If you take 7 plus 5, it is 12. 12 is exactly divisible by 6, right? 12 is exactly divisible by 6. And hence this statement is true. So this statement is true, right? This is a modification of the subset sum problem that we have seen. Here, we are not just looking for a sum to be matched. We are looking for a sum which is divisible by another input, which is m, right? That's important, right? The second case here is, let a given set be 6, 1, 7, where n equals to 3. And let's assume m equals to 5 here, right? What happens now? Is there any subset of numbers that I add here which is divisible by 5? 6 plus 1, 7, 7 plus 7, 14. Whichever subsets I take of this, it is not going to be divisible by 5, right? So this statement is false. There is no way, this instance returns false, because whichever subset I take here, right, its sum will not be divisible by 5. Very nice. The third statement, this is a tricky statement. It says, if n is greater than m, there will always be a subset with sum divisible by m. Okay, this is a statement, and we have to determine if this is true or false. Okay, let's actually take an example so as to solve it, right? I'll prove it also, but I'll not prove it very rigorously, but I'll give you the idea behind the proof. Okay, so let's assume I have numbers like this: 3, 2, 9, 11, and 13. What is my n now? My n equals to 5, right? Imagine my m equals to 4. So what does it say? If you notice, it says, if n is greater than m, there will always be a subset with sum divisible by m, right? So what did I take here? I took n greater than m as we have. Now I'll do one thing. What I'll do here is, I will say set S1, or sum of just the first element is 3. Let me define these variables. S2 is the sum of the first 2 values in the set, 3 plus 2, which is 5, right? So for each of them, I will compute modulo 4. This modulo 4 is 3. This modulo 4 is 1, right? Because what do we want? We want the sum modulo m equals to 0. This is what we want, right? So let me take set S3. Set S3 is the first 3 elements, 3 plus 2 plus 9, 14, right? 14 modulo 4 is 4 3s are 12 and 2, right? Now take S4. S4 sum is 25. Modulo 4 is 1. S5, right? Take all the elements in this set and sum them up. You'll get 38. 38 modulo 4 equals to 2. Now if you notice, how many of these subsets will I have? I'll have n subsets. I'll have n subsets, right? Look at this. I'll have n subsets. Now if any of them is equal to 0, then my problem is solved. But none of them are equal to 0 here. What all are the possible values that I can have here? I can either have 0, 1, 2, up to m, which means I can have at most m plus 1 values here, right? And how many, see, look at this. This is called the pigeonhole principle. There is a concept called the pigeonhole principle that we learn in discrete mathematics. Okay, it's a very simple concept. We don't have to learn rigorously, but the concept is like this. So here I have n equals to 5. So imagine I have 5 slots to fill, right? Imagine I have 5 slots to fill. My m equals to 4. My m equals to 4, which means I have 0, 1, 2, 3, and 4. These 5 values has to be one of these 5 values. Okay, if any of these values is 0, I'm done. Right? Let's assume none of these values is 0. If none of these values is 0, I have 5 slots and I have 4 possible values, which means at least one of these values will be repeated. That's what is called pigeonhole principle, right? Very simple. I'll repeat this logic. Okay, I have 5 slots here, or 5 possible slots here. In these 5 possible slots, since none of them are 0, okay, if any of them is 0, my problem is solved. Then I got some percentile m equals to 0. My answer is true. If none of them equals to 0, I have 4 values here, or m values, and I know m is less than n, which means at least one of these values has to repeat. So in this case, 1 repeats and 2 also repeats. Okay, so let's take the repeating sets S2 and S4. What is there in S2? In S2, I have 3, 2, because it's the sum of the first 2 elements. In S4, what do I have? I have 3, 2, 9, and 11. Now, if I take the set difference between S4 and S2, remember, S2 and S4 have modulo, right? 1 and 1, right? So take that number which is repeating. Because of pigeonhole principle, it has to repeat, right? Now take the set difference between these 2 sets. What do I get? I get 9 and 11. Now this set from basic concepts of modulo operation, this set sum will be divisible by m. Absolutely. You can check that, right? This is 20. 20 divided by 4, the remainder is 0. That's because the remainder of these, see, the remainder of sum of both of them and sum of these 2, the remainder of sum of these 4 numbers is the same, right? Which means, look at this, the remainder here is 1. The remainder here will also be 1, which means the remainder, because of the rest of the 2 numbers, has to be 0. Right? Simple logic of reminders, right? That's why if I take this set of 9 and 11, if I perform modulo m, which is equal to 4, the remainder will be 0. Right? I've just argued this with an example, but the logic stays the same. So this statement is also true, which means whenever n is greater than m, right, you will always have a subset with sum divisible by m. This statement is true. Right? Now let's go to the 4th statement. Now the 4th statement says, if dynamic programming can be applied to solve the above problem, a Boolean dynamic programming table can be created, which will store the status of each of these values, blah, blah, blah. So what it's saying is, I can solve this problem using dynamic programming. Can I solve it? First, let's look at this. Let's look at the problem of subset sum. What does a subset sum problem look like? Subset sum problem with n elements, right? and with the sum that I want to solve. This we already have seen, right, in the course videos. So this is the recursive relation for subset sum. This is equal to false if sum is greater than 0 and n equals to 0. And this is equal to true if sum equals to 0. Otherwise, this is a logical OR of using n minus 1 with a subset with the first n minus 1 elements and sum, or logical OR. We saw this, right? Logical OR. Or let me write logical OR so that you don't get confused. N minus 1 comma sum minus the nth element in my set. Right? This is the recursive relation that we have seen. Right? Otherwise, this is the recursive relation for subset sum. Now I can get the recursive relation for this modified problem. Right? For this modified problem where the subset sum has to be divisible by m, I can get that problem by just replacing wherever I have sum with some percentile m. Everything. So I can represent this whole program as a dynamic programming problem. Right? So I can certainly solve this as a subset sum problem. I can map this as a subset sum problem. Right? So it says which of the following statements are true. 1 is true, 3 is true, and 4 is true, because I can represent this modified subset sum problem by simply modifying the subset sum recurrence relation by replacing sum with some percentile m in this recurrence relation. So S1, S3, S4 are correct. Only S2 is incorrect here. Okay, so this is of course, this problem is actually a combination of lot of stuff. Again, we have a proof here. If you notice, we actually proved this using Pigeonhole Principle. Right? This is a very time-taking problem and certainly non-trivial. Certainly non-trivial. Okay, this is certainly above the gate level, to be honest with you. Okay, just asking this one part will be above gate level. Okay, to be truthful. But that's okay. Let's solve some slightly harder problems because we don't have too many practice problems for DP to start with. Okay, so let's go to the 9th problem. Okay, so this is the rod cutting problem again. I've given a rod of length 10, right? Standard rod cutting problem, the length of each of these rods and the price, right? And I want to find the best solution. Okay, so now actually I can solve this. I can solve this using the recurrence relation. I can solve this using the recurrence relation, or I can try brute force, right? So I can actually try brute force and try to get, so I know that the rod is of length 10, right? So 10 can be broken up into multiple ways. If you solve it using the recurrence relation for rod cutting that we have seen, the final solution that you would get is you would get 2 pieces. You'll get 2 3-inch pieces and you'll get 2 2-inch pieces as the final solution, right? Actually, I worked it out, and when you solve the recurrence relation, you'll get the optimal solution to contain 2 3-inch pieces. So you contain 3-inch piece, 3-inch piece, 2-inch piece, and 2-inch piece. Right? That will be the optimal solution. Right? And if you notice, 3 plus 3 is 6, 6 plus 4 is 10, and the rod length is also 10. Right? And what is the total value that you will get here? So if you take a 3-inch piece, it is 11. So 11 plus 11 plus 2-inch piece is 7. So 7 plus 7, right? 14 plus 22, right? 36. 36 is what you will get as the answer here. Again, for this, there are 2 ways of solving it. Brute force. Brute force is also not trivial here because you have a rod length of 10. If this was smaller, we could have tried brute force like the chocolate example. Okay, it's better. Of course, solving the recurrence relation is also non-trivial because it will take considerable amount of time to solve it. Right? And the final solution will be this. Okay, so I'm skipping the recurrence relation part of it because we've already seen the recurrence relation. I'm not solving the whole bottom-up DP because that will take like half an hour to solve, to be honest. Actually, more than half an hour for this problem. Okay, sounds good. So let's go to problem 10. Again, standard. Okay, this is your knapsack problem. Okay, this is your 0-1 knapsack problem, maximum weight of 14. You're given a bunch of items and values. So we got little tired with solving these DPs. So we found a hack to solve this problem. And the hack is this. Don't laugh at it, please. So the hack is this. We went to Google and we said 01 knapsack problem online. We really got tired with it. Okay. Because we have drawn so many 01 knapsack problem tables, right? We went to Google and we said 01 knapsack problem online. We got a very nice online tool where somebody has written the code for us. Okay. So you just insert each of the items and their weights, right? And you just insert the capacity. It will solve the whole problem and fill the whole table for you, right? It will solve the whole problem and fill the table for you. We actually took this problem because we were so tired of solving these 01 knapsack problems and drawing these tables. We really got tired. We went and put in the numbers here and got the answer literally. Okay. I've also pasted the answer in the solution diagram. Sorry, in the solution doc. This is what you will get, right? I've actually used this website. I just Google searched for it, right? Of course, if you have patience and if you have time, please fill this. This is non-trivial. Look at it. The capacity is 14. So your W is 14. So your table will have 15 columns, right? And you have one, 2, 3, 4, 5 items. So you'll have 6 columns here. So 6 into 14, right? That's almost like 84 cells to be filled. And you got to be careful not to mess it up, right? And when you fill it up, you'll finally get a knapsack value of 124. By the time we reached here, we got tired of doing these tables. So we used an online tool to do it. Okay, to be honest with you. Okay, sounds good. Of course, in the examination, you don't have this at your disposal, but that's how we got the answer for this problem. Okay. The important part, remember, the important part is to know the recurrence relation. If you know the recurrence relation, you can always solve these problems. My suggestion in an examination setting, my suggestion is this. If you have solved every other problem, if somebody gives you a problem like this, which could take anywhere from 10 to 15 minutes at minimum, even if you know the recurrence relation at heart, and it's very, very error prone. This thing can be extremely error prone. Even if you have spent a lot of time, one small mistake, everything goes for a toss, right? Only when you have ample amount of time, you have solved every other question comfortably, then please go and solve this question. Otherwise, do brute force, right? And for some, otherwise just do brute force. That's also okay, to be honest, for problems like this, right? See, here we can do some form of brute force, right? Because I have 10. See, what is my total capacity? 14. I can do some form of brute force here, right? 10, 2, 2. This is one possibility, right? I can't do 10, 6. I can't do that. I can do 6, 2, 2, 1. I can do that. That's valid, right? So if you notice, I can do 10, 2, 2. I can do 10, 1, 2, right? Or I can do 6, 2, 2, 1. Right? There are only a few possibilities here. And if you notice here, the final solution you'll have is value 29, value 25, right? Weight 1, 2, and 10. Look at this, 10, 2, 1. This is the solution that you'll get even after solving BP, right? So now, instead of trying all the possibilities, what all possibilities do I have? I have 10, 2, 2. I have 10, 1, 2, right? Or 10, 1 and this 2, or 10, 1, the other 2. 10, 1 and the other 2, or I can have 6, 2, 2, 1. Right? Just 4 possibilities. Just keep filling the values and pick the best one. So sometimes if you have fewer items to experiment with, it's easier to just solve it using brute force. Okay, sometimes that's a much faster way than drawing the whole DP table. Okay. So let's go to the 11th question. Okay, this is an interesting question. Okay, so this question is called, okay, this is also a new concept. I'll explain you very quickly. This is actually an easy problem. So this is called a multi-stage graph. Why is it called a multi-stage graph? This is called as stage 1. If you look at this, all the vertices in this stage are at stage 1. All these vertices are at stage 2. All these vertices are at stage 3. All these vertices are at stage 4. This vertex is at stage 5. And edges only go from one stage to the other stage. Look at this. And that to do only to the next stage. They don't jump around, right? Yeah. So edges go from stage 1 to stage 2, or stage 2 to stage 3, or stage 3 to stage 4, or stage 4 to stage 5. Right? This is the only way your edges will be formed. This is called the multi-stage graph. This graph is called the multi-stage graph, wherein I can break my set of vertices into stages, I can break my set of vertices into stages such that all edges go from one stage to its succeeding stage, right? So this is called a multi-stage graph. Okay. So in a multi-stage graph, I want to find the minimum path or minimum cost path from vertex S to vertex T. Right? I want to find the shortest path. Now, how do we find it? Actually, we can write this as a dynamic programming problem. Okay, let me explain you logically how it works, right? So the shortest path from S to T is the shortest path from S to G. Look at one. So this is at stage 1, stage 2, stage 3, stage 4, stage 5. Right? My source is at stage 1. My destination or my final destination is at stage 5. Right? So to find the shortest path from S to T, if I find, so the shortest path from S to T is, if you think about it, it is the minimum path amongst the shortest path from S to G, shortest path from S to G plus G to T plus weight of GT, right? Because a path from S to G and then going from G to T, that could be the shortest path, or the shortest path from S to H, and the weight of H to T, the weight of the edge from H to T, or the shortest path from S to I plus weight of IT. Between these three possibilities, pick up the minimum possibility. Let's assume, hypothetically, let's just assume, just for simplicity, that the shortest, that H, so this will tell me whether G belongs to the shortest path, or H belongs to the shortest path, or I belongs to the shortest path. And now I'll recursively solve this, right? I'll keep recursively solving this, right? And this is the recurrence relation that you would get here. If you actually solve this problem, you will actually solve it using this recurrence relation, right? So you'll try to find the shortest path. Again, here you could have applied Dijkstra's algorithm, right? Here you could have applied Dijkstra's algorithm because all the edge weights are positive, right? You could have applied Dijkstra's algorithm, then you would have found shortest path from vertex S to every other vertex, but that's not what we want. We can do it much more optimally using this structure of a multi-stage graph, using this property of a multi-stage graph. And this is how your recurrence relation will look like, right? Now the shortest path from S to G and S to H and S to I will have some overlapping subsolutions, right? So this problem actually has the optimal substructure and the overlapping subproblems. Now, of course, you got to solve it manually. And when you solve it manually, right? When you solve it manually, I've actually solved it manually. So, so the question here, the question is here. I forgot to read the question, sir. I got so excited, I forgot to read the question. Okay, the question here says, the number of minimum cost paths. It is not asking us the cost of the path. That I can find with Dijkstra, right? I can find the cost of the shortest path using Dijkstra. But here it's asking me to find the number of minimum cost paths. To do that, I have to literally solve this dynamic programming problem. Okay, using the tabular approach or using the brute force approach. Okay, and when I solve it, so when I solve it, okay, so just let me change the. So when I solve it using using the dynamic programming or brute force, I will get the minimum cost length to be 18, and I'll get two paths, SECGT and SCEIT. Okay, both these paths are of length 18. Okay, so here also I'm skipping the actual solution because drawing the dynamic programming table is non-trivially expensive. Okay, so let's go back to our question here. Each of these problems can take like 20 to 30 minutes. Okay, the reason we still gave these problems is so that you'll figure out the, see, in dynamic programming, the most important thing is to figure out the recurrence relation. If you learn to figure out the recurrence relations, and if you learn to figure out the optimal the overlapping subproblems, the overlaps, right? Remember, dynamic programming is one of the most favorite type of algorithmic interview questions that are asked by top-notch product-based companies. If you go to a company if you go to Google or Microsoft or Amazon or Facebook, any top-notch company for a product, as a software engineer, if you go for an interview, they would most likely give you at least one dynamic programming problem as part of their interview loop. Okay, and there are hundreds of DP problems, right? So we just wanted you to acquire that skill to be able to solve these recurrence relations and to be able to figure out the recurrence relationships and to see the and to be able to figure out the overlaps. Okay, so that was the whole objective here. Okay, I know some of these questions are outside the realm of GATE, but who knows? They could give a multi-stage graph next year, right? There is no limitation on, because they just say dynamic programming is part of the syllabus without telling what topics are part of it. Okay, so this question. So it says, consider that we are using the Bellman-Ford algorithm for computing shortest paths from single source vertex to all other vertices in the weighted digraph with n vertices. Okay, so I have the source here, right? And while performing the algorithm with its dynamic programming paradigm, which of the following is the correct number of candidates for an optimal solution to a subproblem involving the destination V? Right? Suppose, imagine if I'm trying to find the shortest path from S to V. This is my destination and this is my source, right? Now, imagine I can imagine to go from S to V, right? I could have some other vertex, let's say V1, wherein I have an edge to V. Similarly, I have a vertex V2, which has an edge to V. Similarly, let's say I have a vertex V3, which has an edge to V. Right? If I want to solve the Bellman-Ford algorithm here, I could say that I want to find the shortest path from S to V1, right? So how many subproblems are you solving, right? So this is one way of looking at the shortest path, right? I can look at the shortest path from S to V because I only care about vertex V here. I could think of the shortest path from S to V as, what are the subproblems here? Look at the question it asked. Which of the following is the correct number of candidates for an optimal solution to subproblems involving the destination V? Which means to solve this with V as the destination, how many subproblems do I have to solve? Imagine if V is connected to 3 vertices here. Let's assume V is connected to 3 vertices, let's say. Okay. If there are 3 edges coming from other vertices to V, that is called the in degree of V. Okay, that is called the in degree of V. In degree of V is the number of directed edges that are starting from other vertices but are landing at vertex V. That's called the in degree. Right now, the number of subproblems that are involved in solving the shortest path from S to V is equal to the number of shortest paths in the number of shortest paths. The number of shortest paths. Sorry, let me repeat that statement. Tricky. Okay, to find the shortest path from vertex S to V, I have to find 3 other shortest paths from S to V1, from S to V2, and S to V3. So there are 3 subproblems that I need to solve, right? To find, and once I solve these 3 subproblems, I'll take this path length plus this edge length, this path length plus this edge length, this path length plus this edge length, and I'll figure out the minimum, right? So if V has an in degree of 3 here, which means if it has 3 vertices from which it has an edge, a directed edge, then I have to solve 3 subproblems as part of the dynamic programming paradigm, right? So the answer to this question, that's what it's asking here. It's asking how many subproblems do I need to solve if I want to find the path from S to V. I think there is a typo in this answer. We need to change this. It should be in degree of V, not 1 plus in degree of V. Okay, so I think we'll correct this typo. I think it is in degree of V, not 1 plus in degree of V. Okay, I hope this is clear, right? Very simple argument. This is how you can define the recursive solution, right? For shortest paths. This is one way of defining it. Okay, so let's go to question 13 now, right? So okay, let's go to question 13. Okay, this is your TSP problem, right? This is your TSP problem, right? So what are you given? A traveling salesperson has to visit 4 cities. He wishes to start at a particular city, visit each city, and then return to the starting point. The traveling cost of each city is given in this box, which is the minimum cost of the salesman's visit. Okay. Again, recursive problem, right? If you think about it, this is basically the recursive problem, right? So there is one hack that we can apply to solve this faster. Okay, this is a recursive DP problem. You can draw the whole DP table and all of that, but there is a shorter way. First, let's see, because I'm given 4 numbers here. The hacky way of doing it is, can I find a traveling salesman tour or the whole path starting from some vertex and reaching the same vertex? Can I find it with length 200? Okay, let's do brute force. Let's assume I start with A. Okay, so I tried all the options. So you can manually try from A. If I go to C and then I go to B, then I go to D and I go to A. Okay, so what is A to C? A to C is 60. C to B. C to B is 40. Right? C to B is 40. Then B to D. B to D is 50. D to A. D to A is again 50. Okay, so there are many such paths. Remember, because you have 4 vertices, there are many such possibilities that you have to be careful about. But through brute force, one way is to actually solve the DP way of doing it, using the recursive solution, the whole thing. The other way is to do brute force. Let's try with 200. Okay, I tried multiple options and I found this path wherein I'm starting from vertex A and reaching vertex A again, and the sum of my paths is 200. Okay, so obviously I want the minimum path, right? So if 200 is possible, 200 must be the answer, right? This is again a brute force way of solving it. Took me a while to figure out these options. And of course, this is also error prone if you do brute force. You got to be careful. Okay, and trying out all the options is non-trivially expensive. Okay, so your call, whether you want to do the DP table or you want to do brute force is up to you. If anybody knows an easier way to solve this problem, please do let us know, because I couldn't come up with an easier way or a shortcut to see many of these problems. I couldn't come up with shortcuts for these problems. Okay, so there are some heuristics, there are some approximate algorithms and heuristics for TSP which are beyond the scope of this course, and hence I did not apply them to solve them. Okay, there are some very nice heuristics and approximate algorithms for TSP, because we know TSP is an exponential time algorithm. There are some approximation algorithms which are beyond this course, beyond the scope of this course, and hence I'm not going down that path. Okay, sounds good. So let's go to 14th problem. Okay, so where is my 14th problem? Okay, so okay, this 14th problem is, consider the values and weights of 5 items listed below. You have 5 items, their values and weights. The task is to pick a subset of these items such that the total weight is no more than W. This is the capacity. Okay, moreover, no item must be split. Okay, the total value of items picked by an optimal algorithm, let's denote it by VOPT. A greedy algorithm, we've seen. So actually, this problem, we have actually solved this very similar problem with slightly different weights. I think in the greedy in the greedy algorithms chapter, right? I think we solved this in the greedy algorithms chapter, right? So today, whatever content that you're reading today in the greedy algorithms, you would have encountered this problem, or a problem very similar to this. We have actually solved it step by step. Okay, this problem is exactly the same as the one we have in our solved problems. I think this solved problem is there after, if I recall, fractional knapsack. I think this problem is there after fractional knapsack. Okay, this is a solved problem, exactly the same problem with different numbers. Okay, so what it asks us is VOPT minus V greedy. Okay, whatever strategy that we have explained in that video, just reapply that, because I've not yet covered what greedy algorithm here is, right? So once you cover greedy algorithm, you'll be able to answer this, and the answer is also shared with you. Answer will also be shared with you in the doc that we are sharing. Okay, so the answer will be 11, but I don't want to go into the greedy algorithms because this practice session is not about greedy algorithms, right? So, but very exactly the same problem, just the different numbers. I hope they're different numbers. I hope I did not solve the same problem. So it's there in it's there after the fractional knapsack video, right? As a solved example. So you can just go down that path. Okay, so I'll skip it for now. So the last problem is problem 15. Okay, it says, consider the following statements. This is a good problem. This is of the gate type. This problem is of the gate type. Okay, it's actually a good problem, right? So consider the following statements. It is possible for a dynamic programming algorithm to have exponential running time. Yes, why not? You have traveling salesman problem, right? Which is a DP, which has exponential time complexity, right? So this statement is true. What about statement 2? If a dynamic programming has n subproblems, then its running time is order of n. No, this is false. Because each of the subproblems need not be order of 1. Right? Each of the subproblems need not be order of 1. If you think about it, your longest common subsequence, right? Right? It has n subproblems, but its time complexity is not order of n, right? So it's not necessary. The third is in a DP algorithm for knapsack. Okay, this is 0, 1 knapsack. Okay, since for each item I, the recurrence considers both cases of adding an item I or not. The algorithm inevitably calculates the cost of possible subsets of n items. Okay, this is a good statement. So what it's saying here is if I have n items in a 0, 1 knapsack, if I'm going to inevitably calculate the cost of all possible subsets, how many subsets do I have? I have 2 power n subsets, right? The total number of subsets is 2 power n, which means it's saying that your knapsack algorithm, your 0, 1 knapsack algorithm will anyway compute all of these subsets anyway, even the DP algorithm. So the time complexity is order of 2 power n. That's what it says. But that's not true, because the dynamic programming algorithm for knapsack has a time complexity of order of n into w, where w is the capacity of the knapsack. Imagine if w is significantly less than 2 power n. We've discussed this case, right, in the course videos. If w is significantly less than 2 power n, the time complexity that you have here is going to be significantly less than order of 2 power n, right? Which means I'm not, see what it says, in all cases, see, it is possible that if w is order of 2 power n, right, then obviously this statement is true. But it says inevitably, which means every time its time complexity is order of 2 power n, which is incorrect. Because if your w is a small value, then your time complexity is order of nw. So this statement is also false, right? So what does it say? Which of the following statements is incorrect? S2 and S3. So option 4 is the right option here. So this question is a very good question, because this is not asking you to do a brute force thing. This is asking you intuitively, your understanding of dynamic programming, without actually forcing you to solve a DP bottom up. Okay, I hope this is clear. And we'll share the document. Yeah, our team will anyway share the whole document with you. Just give me a second. So I'll stop the screen sharing. Yes, so once again, I just wanted to let you know that we have skipped some of the DP tables, because each of those tables, as you have seen in the solved problems, could take half an hour to solve each of the problems, right? And it's impossible to solve in 1.5 hours to solve all of the problems that we have. Hence, we have resorted to pre-solving it and showing it to you here, right? Ideally, I would have loved to show you how to do it, but it's a constraint of time. We'll share the detailed solutions. Try and practice it in your own time, number 1. Number 2, whenever you're given a DP problem, try to solve it using brute force, because sometimes that will be much faster. If you cannot solve it using brute force, or if it's not possible to solve it using brute force, postpone solving that problem in an examination type setting, because otherwise you'll spend a lot of time stuck at one problem, 10 minutes, 15 minutes, even 20 minutes, right? And ideally, for a 2-mark question in GATE, you should avoid spending more than 5 minutes. Preferably, you should solve it in 4 minutes. Right? So if you're spending significantly more than that, you should try to avoid it and come back to that if you have ample time left at the end of the exam. Right? That's my strong recommendation. And the reason we gave some of these assignments, some of this slightly, see, this is certainly much harder than GATE level, because there are very few questions in GATE level. It's not hard because it's intuitively hard, but it takes a lot of time to solve. It's laborious, if you have to use the right word. It's not hard, it's laborious. Okay, folks, thank you very much for joining us today. Again, I just wanted to mention that we are almost done with data structures algorithms. We have a couple of videos in greedy algorithms, and we have a very simple concept called complexity classes that we'll cover briefly here. because the same topic will revisit in theory of computation in much more detail, right? In theory of computation, we have to revisit the concept of NP completeness, NP, all of that in much more detail, right? We just wanted to cover it in algorithms, even though typically it's not in algorithm syllabus explicitly in the GATE. We wanted to cover it for completeness. So we'll touch upon it, give you some brief idea, revisit in theory of computation in detail, right? So hopefully by tomorrow, end of day, or worst case by day after tomorrow, you should get all of the content. And if we add any new content, we were thinking of adding a few pieces of content here, reorganizing some of the content. For example, some of you have asked for proofs, right? Or at least logical understanding for all of your graph algorithms. In the greedy chapter, we'll see the intuition behind Prim and Kruskall's algorithm, right? We'll also see, we've already seen in the dynamic programming for Bellman-Ford and Floyd-Warshall, right? We've seen the logical intuition from a dynamic programming perspective. So we were thinking we'll reorder some of these so that it's better for you to grasp it and to revise it in the long term. Whenever we make a revision or anything, we'll inform you and reorder the videos in such a way that you're not confused, number one. Number two is there are some small miscellaneous topics here and there which could help you solve questions faster, okay? Like a number of binary search trees and its relationship to Cayley's number. Of course, some of these concepts are also in counting and discrete mathematics, but we thought we'll just list all of those topics as some additional topics, okay? And most importantly, we'll be starting C programming as our next subject from April 3rd. Before that, since we'll finish most of the content by day after tomorrow, we'll have two subject tests, each with about 30 questions. Okay, because in GATE, you would roughly have about, basically we want to have 30 questions per test, and each test would be 1.5 hours long. So we would ideally want you to solve these in 1.5 hours each, so that you practice. And the questions will be from the whole spectrum, and we'll give weightage based on previous GATE question papers. Okay, we'll not ask you just, so we'll try to, so this is like a subject revision. Until April 2nd, end of day, please revise all the concepts. So I know that some of the students are lacking behind. Please catch up. That's a fundamental reason why we are giving this a 3-4 days gap, and also practice questions. Please catch up with us and let's get started with C from April 3rd morning onwards, right? So, and we got to speed up slightly now, so that because we have done one subject, we will be speeding up, and of course we'll give you enough time for revision, practice, all of that. But we need to start putting in more effort from our side to stay on course, right? Because we have talked to many students and some of them are lacking behind, some of them want slightly more time, right? We also see how many people watch each of the videos. We also check out for how many of them are solving the practice problems, how many practice problems they're solving, all of that statistics, right? We understand that you're caught up in some miscellaneous work, but please take time. See, we are giving you time till the 3rd of April to catch up, finish whole of data structures algorithms, and start afresh and try to stay on track with us from April 3rd for C programming language. Okay. See you folks. Thank you. See you again on Saturday. Bye-bye.